Hello and a very good morning to all of you. Today we'll be doing a chapter of circles class 9th. First we'll be doing some basic definitions and then we'll proceed on to the theorems of the chapter. Right? So let's proceed. The first definition that we have, that is what actually is a circle. Right? A circle is a collection of all points that are equidistant from one point that is also known as the center of the circle, right? It is a collection of points which are equidistant from one point. Equidistant from one point. The next important definition we have is of the chord. What is a chord? A chord is simply a line segment joining two parts on the circle. Clear? So in this diagram I can take 2 points A and B and I draw a line segment connecting them. So this will be a chord, AB, right? And one important thing I forgot, that how do we actually denote a circle, right? We denote it by simply writing a C for circle with center O and radius R. So here O is denoting the center and R means the radius of that circle. Clear? Third point, or rather which is a sub point of this A part, which means what is a diameter. You all must be knowing that a diameter is nothing but it is the longest chord of the circle. Right? It is the largest or the longest chord of the circle. And it always passes through the center of the circle. Clear? And a circle can have infinite diameters. Clear? Now the sub part of diameter, what is that? That is A1. We call it as the radius of that circle. What is radius? It is simply R, radius, is half of the diameter, right? Again, there can be infinite radii in a circle. Please note that the plural of radius is what? Radii, R-A-D-I-I. Moving on with the third point. Now we'll be moving to some technical parts of the circle. That is what an arc. What is an arc of the circle? Again, let me draw it a bit more neatly. Oh my god, I just messed it up. A circle with center O, and again I take 2 points over here, A and B, and highlight this continuous part on a circle. Right? Now this is what? This is an arc. So what is an arc? It is nothing but a continuous piece of the circle. Now you might notice that okay, this is a continuous piece of the circle AB, but what about the remaining part? Well, the remaining part is also an arc, right? But what is the difference? That the smaller arc is called as the minor arc and the larger one is called as the major arc, right? So there are two types of arcs. One is minor and one is major arc, right? I hope this much is clear to you. Moving on. Now the fourth definition, again using all the definitions, we'll be defining what are segments and sectors of a circle. So fourth point, what is a segment? Again, I take a circle with center O. What is a segment? If I draw a chord, let us say P, Q. So a segment is an area or a region bounded by a chord and an arc, right? So a segment is an area or a region bounded by this chord PQ and this arc PQ. So this all is a segment. But again, there are two types. One is what? The minor segment, and this bigger one which I am shading with dots, this one will be known as the major segment, right? Moving further, the fifth thing that we need to define, that what is a sector. So a sector is again an area or a region bounded by what? An arc and two radii. So for making a sector, what we have to do, we have to take an arc, let us say again P and Q, and we have to join OP and OQ. Clear? So this dotted region is defining one sector of the circle, enclosed by an arc and two radii, again of two types. This one is called as the MI minor, and this one MA is the major sector of the circle, similar to a slice of a pizza, right? Sixth point, what is that? That is a secant. What is a secant? A secant is a line joining two points on a circle. Now you may be wondering one thing, that the definition of a chord and a secant is almost similar. So what is the difference between the two? Well, in chord we use the word a line segment, and in secant is simply but a line. So if I again make a circle, here I make a line, let us take it A and B. Now this is a line, right? This can infinitely extend in both the directions. This is a secant AB. This is a line segment joining two points known as the chord A dash B dash. And the seventh point, we have to define what is a tangent. A tangent is again a line touching only one point on a circle. In the same diagram, I shall make a tangent too. Now here, it is a line infinitely extending in both the directions. Let this be P and Q, and it is only touching one point. Let this be R. Clear? So we have here a chord, a secant and a tangent, right? I hope this much is clear to all of you. Now proceeding further, we'll move on to the theorems of this chapter. So moving on, our first theorem, theorem number 1, what it says that equal chords subtend equal angles at the center of the circle. This is the statement of our very first theorem. So let me draw a diagram for you. A circle with center O. Let this be a small o, and let me take two chords which are equal. They don't look equal, but actually they are equal, AB and CD, right? And join these 2 points, OA, OB, and two other points OC and OD, right? So what is given to us? Given is two chords AB equal to CD in a circle with center O and radius R, right? Now what we have to prove? What we have to prove that angle AOD and COD, that is the angle subtended by both chords at the center of the circle, are equal. Angle AOD is equal to angle COD. Do we have to do any constructions? Yes, we have to do. What is that? Join OA, OB, OC and OD. OC and OD. Now, the proof is very simple. What is the proof? We take two triangles AOB and COD. In triangle AOB and triangle COD, OA is equal to OC. Why? Because they both are the radii of the same circle. Now OB is equal to OD. Why? Because again, same reason, radii of the same circle. And AB is equal to CD. That is what? That is given to us. So now we can say by triple S congruency theorem, triangle AOB is congruent to triangle COD. Okay. And now we can say angle AOD is equal to angle COD by CPCT, corresponding parts of congruent triangles, right? I hope this much is clear to all of you. And the next theorem we'll be doing is theorem number 2. It is just the converse of this theorem, right? Like in this theorem, we said that equal chords subtend equal angles at the center. In this, we'll be doing that if chords subtend equal angle at the center, then they are equal. Simply converse of it. So theorem number 2, if two chords subtend equal angles at the center of a circle, then they are equal. Right? Again, let us make a diagram. A circle with center O, two chords AB and CD. The diagram will be almost the same, right? But now for the sake of convenience, I will take angle AOD and COD as angle 1 and angle 2, right? So now what is given to us? Given to us is angle 1 is equal to angle 2 in a circle with center O and radius R, right? What we have to prove? We have to prove the converse of it, that AB is equal to CD, right? Now what we need to change is, construction will be same. Again, in triangle AOB and COD, AO is equal to OC, OB is equal to OD, they are radii. But since this we have to prove, so we can't use this. Instead of this, we will use angle 1 is equal to angle 2, that is given to us, right? And over here, our condition will change. Now, this angle 1 comes in between two sides, AO and BO. So we'll be using SAS, congruency condition, and here what will be equal to each other by CP CD, that will be AB will be equal to CD by CP CD. As simple as that, right? I hope it is clear to all of you. Moving on. So moving on with the third theorem, we have a line drawn perpendicular from the center of a circle to a chord bisects the chord, right? Let me again draw a circle with center O. So I take a chord over here, A, B, I draw a line perpendicular to it, right? And I do little construction over here. So what I'm given a circle, center O, radius R. Let's take this point as OC, and OC is perpendicular to AB chord. What I am to prove? I have to prove, let this be angle 1 and this be angle 2. I have to prove that AC is equal to BC. Construction, yes. What? Join OA and OB, right? What is the proof? Now if you just look at the figure, you might remember it that you have done similar figures in congruency of triangles. The only difference is that now this figure is enclosed in a circle, right? So in triangle AOC and triangle BOC, first of all, OA is equal to OB. Why? They are radii of the circle. Angle 1 is equal to angle 2, 90 degree. That is given to us. Now OC is equal to OC. Why? That is the common side. So what condition we have? By right angle angle, hypotenuse and the side of the circle, triangle AOC is congruent to triangle BOC, right? Therefore AC is equal to BC by CPCT. Very simple proof. I hope this is clear to all of you. Moving on to theorem number 4, that is again the converse of it, right? So now if converse of it, what we have to prove? We have to prove what is given to us. Again, we will write here, we have to prove that OC is perpendicular to AB, and what we are given is AC is equal to BC. Right? Now what we'll be doing, we'll be changing our statement. Theorem number 4. a line joining the midpoint of a chord to the center of the circle is perpendicular to it, right? The diagram will again be the same. Join O, A and OB, same construction. So now OA is equal to OB, that are the two radii. Now this angle 1 and angle 2 are 90 degree, we have to prove, right? Again, OA is equal to OB radii. Since we have to prove this condition, we cannot write given. What we can write is AC is equal to BC, because that is actually given to us. And by RHS, these two triangles are congruent to each other. And now we can write that angle 1 is equal to angle 2 by CP CD. Angle 1 plus angle 2 make a linear pair because they lie on a straight line. Therefore, if we take 1 as x and 2 as x, 2x is equal to 180, or x comes out to be 90 degrees. So we write here angle 1 is equal to angle 2 is equal to 90 degrees, right? I hope this very simple converse of the previous theorem is also clear to you. Thank you.